You see my screen?
Yeah, everything looks really good.
Yep.
I'll just wait for a ping from Lena. All right. Thanks everybody for tuning in. Hello and welcome. Today we are joined by Richard Blair, the VP of Software Engineering here at Hedera, and Danno Ferrin, who's our Principal Software Engineer. And we're going to talk a lot about the Smart Contracts 2.0 and the increase in capabilities of the Smart Contract Service. So, as usual, feel free to ask questions in the chat and we'll get to them at the end of the presentation. We're going to start off with Danno giving a presentation and then we'll segue into Richard's slides. All right, shall you guys take it away?
Yes, and oh my goodness, the lights just...
Emergency lights.
Mute, Danno.
Okay, I know I'm muted. All right. So hi, I'm Danno Ferrin. Like I said, I'm one of the principal engineers here at Hedera Hashgraph. Bit of background. I didn't put a background slide about myself, but I think it's relevant to some of the stuff that I'm going to talk about. So I came into Hedera a few months ago, and one of the tasks I've been working on is improving the EVM ergonomics of Hedera. And as we're going to slides, we'll go into details of what that meant. But before I was at Hedera, I was at Consensus for about 2.5 years, and I was a core developer on the Hyperledger Basu project. And Hyperledger Basu is a pure Java implementation of the Ethereum protocol, mainnet compatible, and it's also got some enterprise features in with it. But what's important is that it's Apache 2 licensed, and it's written in Java, and it has an EVM library. So we were able to take that. Well, I'll save that until I get to that point late in the slides. But that's where I came from before I came here. I think EVM and smart contracts are super cool, very neat technology, and I enjoy programming in it. So first, I'm going to talk about smart contracts, what and why, and then yesterday, today, and tomorrow of what was going on with the smart contracts inside of Hedera. And then we'll have a segue to Richard Bair because there is also a deeper issue, more than just smart contracts, that enables high-performance smart contracts, and that's the storage behind it. And until you've really worked on the client side, you kind of get a clue of how important storage is, but when you worked in it, you realize the storage really is, just as important as the EVM execution itself. And it's actually the secret sauce to well-performing clients. So Richard will talk about that after I talk about EVM itself. So smart contracts, what and why? Hedera is already a nice full functional platform that gives you tokens and consensus services and file storage, high transaction throughput. So why smart contracts? Well, first, let's get a bit of a context of what a smart contract is. This is according to Wikipedia. Sorry, I'm using it as a primary source. You can get the citations there. But it's something that automatically executes, controls, or documents events and actions according to the terms of contract and agreement. In this case, it's going to be the EVM opcodes. It has a very clear and definite description of what that state machine does. And when you do it this way, it reduces the needs of trusted intermediaries versus other smart contract platforms like Fabric, where you execute your smart contract, you get 3 or 4 people, or whatever you have it set up to agree, this is the correct answer to it, and then they put it in. And that works in most cases, allows you to do more complex things. But if you want to have a situation where you only need one trusted, you only need one honest person to say what the smart contract does, that's where a specification-driven smart contract platform like the Ethereum virtual machine really helps. And it helps, arbitrating costs, fraud losses, and it sets very clearly, this is what it said, this is what it does. And it can be executed without either one of the parties necessarily being involved. So a smart contract, I'm trying to find my keys, there we go. So one thing is to look at in a smart contract is to look at the locale of execution. Where are you executing it? And this is what we have set up in Hedera today. Your user experience is in your web browser or your mobile app. Your business logic is in the cloud server, and the ledger data is stored in the distributed ledger. Your business logic manipulates your tokens, manipulates your consensus messages. You might run another blockchain off of it in your business logic. Smart contracts takes that execution and moves it inside of the ledger. So it moves that business logic and it moves that logic that goes with it, and it's executed in the ledger and it's distributed, and make sure that it's executed consistently and reliably and deterministically. So we take this locus of execution, we move it in. Now, one of the cool things about this is you can still keep your business logic on top of it. And there's a lot of Web3 type applications that do this sort of approach, where they put the consensus critical, ownership critical items in the smart contract on the ledger, and all the fancy entertaining stuff that isn't necessarily consensus critical, that isn't driven by ownership, isn't driven by mutual agreement on a state, is pulled out. And then of course, the user experience can live on the website. So what sort of things might you want to do with a smart contract? And here's, I think, the top 5 types of categories that people implement with smart contracts. Probably the top 2 things are stuff that Hedera supports natively. Those are stablecoin, those are tokens and NFTs. And a couple of interesting uses for tokens beyond simple, simple who owns what is the notion of a stablecoin, where the value of the coin and the amount of coin that is in circulation is controlled by various other external rules you put into the system, and it moves the token balances around, and usually in the intent to keep it tied to a particular currency amount. Another thing is they'll wrap assets. You want to trade Bitcoin on the Ethereum blockchain, you wrap it in a token. NFTs is another example. Instead of doing fungible tokens, you might have a profile picture. Those are the current biggest trend in NFTs right now. There was a YouTube video also where ownership of the NFT corresponds to ownership in the YouTube video. That's already been put out there. But I think, some of the more interesting things that we're going to see in the future that are more useful to end users are the next 3, particularly the next one. Games is an excellent example of where you might use all 4 locales to execute on it. Axie Infinity is one game, and Gods Unleashed is another such game. It's kind of a Hearthstone version where the ownership of the cards is managed on the blockchain, but the playing of the game is maintained off of it, and you have to own the cards to play the game. DeFi is another example where you can actually trade between them and do interesting things. Uniswap manages a bunch of random pairs and does bonded curves and a bunch of stuff I don't understand, but the finance people are super excited about it. And Compound lets you, I think that's the one that lets you do loans against your currency and pay it back, and manages it all online without needing a banker. And another growing area is something called a DAO, a distributed autonomous organization. 2 DAOs that I find interesting. One is the Moloch DAO that is there to take people's money, and then they have votes to say which projects they send it out to build various Web3 type projects. And another one, Spork DAO, which is the one that is taken over ownership of a conference that I like to go to, ETH Denver. They're changing it to Spork, some sort of a new name like Colorado Jam. It's because they're broadening way away from Ethereum because there's a lot cooler stuff going on in the Web3 space than just Ethereum. So they've renamed it Spork DAO because Sporks is one of their mascots, in addition to buffacorns and marmots with monocles that skydive with VR helmets. So it's pretty interesting stuff. So where were we with Hedera with smart contracts? Hedera's had smart contracts for quite a while. And the way it was implemented was with a library underneath it called Ethereum J. Ethereum J was one of the first Ethereum clients that was out there, along with Geth and C++ Ethereum and Python Ethereum. And so what Hedera did is they took as much of it as they could, and they tried to use it as much as a library as much as they could. So they would take the data that would be stored in Ethereum J, and instead of storing it in its storage, we stored it in what we were doing with Hedera. We were able to intercept that. And we were able to get it in so that with a smart contract, you could send and receive HBAR within it, store your smart contract data. Now, one important thing that was different when we took the library out from Ethereum J and used it in Hedera is we gained a lot of the advantages Hedera had that distinguishes Hedera from Ethereum. And the biggest thing is there's no server transaction ordering. There's no block production that we're bringing over. There's no memory pool management. And so one of the nice side effects we get from that is that there is no maximum extractable value or minor extractable value by the nodes. They don't pick and choose which transactions they do in which order. It's dictated by the protocol, And there's basically none of the sandwich trading games that go on with Hedera, because by protocol, you do it in this order, and that's, no one gets to pick the order. Now, it served great for a while, but it's grown up to have a couple of drawbacks. About a couple of years ago, 3 years ago at this point, the developers stopped maintaining Ethereum J. They either joined consensus and helped with Hyperledger Basu, and the remainder of them went and worked on Ethereum 2.0. And they officially sunset the library. They did this shortly after Petersburg came up in the first quarter of 2019. So as a consequence, there is a couple of forks, or 3 forks. There is Muir Glacier, Istanbul, and London, and upcoming Arrow Glacier hard fork that they don't support. And there's a couple of interesting EVM features that were added in London that are kind of useful and valuable. But as a consequence of this also, that means that they only support older versions of Solidity, can only guarantee that Solidity up to version 5 point, whatever the latest is, will generate bytecode that we know will be compatible with EVM. So that was yesterday. And let's push the button. Today, we have migrated to Hyperledger Basu as the library and gone off of Ethereum J. It has some advantages. It's under active development. Officially, it's a project at the Hyperledger Foundation, formerly the Hyperledger project. It started out as a project at Consensus, and I worked on that for a couple of years. It was called Pantheon at the time. And like Hyperledger does when it brings in a new project, it gives it a new name. So the new name for the exact same code that we were managing before is called Hyperledger Basu. And it's done an open source development, much like the Hedera services are. We have people from multiple companies. I still am active on it, not as active as I used to be, but I'm responsible. I've kind of taken ownership of the EVM portions of it, particularly to split out the library from the Basu. So when you use the EVM in Hedera, you only need to bring the library portions of it. You don't need to drag everything on with it, like block production and proof of work mining. So the only thing we have to ship with it are the libraries essential to the Ethereum virtual machine. It's faster than Ethereum J. That's something that we were there before, and I've spent to make it even faster than Ethereum J. So that's going to help us keep more transactions going through at a time. It supports current mainnet specs. Currently, we're at London. London is the current active mainnet spec. The mainnet itself is going to have an Arrow Glacier hard fork that only affects something called the difficulty bomb that is only on Ethereum mainnet. It doesn't affect anything in EVM. So that's great for us. So we'll be able to keep up support with it. It supports current Solidity versions. Solidity is up to version 0.8.10, supporting all sorts of interesting, there's a new version of ABI v2 needed for decoding. There's all sorts of ergonomics introduced in the language. And because we're up to date with the mainnet specs, we know we can support whatever Solidity is going to spit out. And the biggest thing is that we're going to support future EVM developments. And I think that's the next slide. Yeah. So we're going to support future EVM developments. And like I said, we took this as a library out of Basu. We only have to support the EVM portions of it. And there's lots of great opportunities to use this EVM library in whatever your Java-based project is. Hedera Hashgraph and Basu will continue to use it. So it's going to continue to get greater and greater as it goes on. So as far as potential EVM changes that using this Ethereum library might support in the future, things to look forward to, I've identified 4 main things that are on the horizon that might actually ship in 2022. No major changes are going to come the rest of this year, and nothing's going to come in the first half of next year. So these are the things that might happen in the second half. The biggest thing that's almost certainly going to happen is something called the EVM container format. The way that the EVM bytecode is shipped is going to change to make it more validatable, more verifiable, more consistent, quicker to use, more reliable. So you don't have to do jump table analysis every time you do a jump. You don't have to worry about running into opcodes you don't know because it's not going to deploy. That validation is coming up there. And the second point is the validation. Because of that container format, they can put some interesting validation things. And honestly, they're learning a lot of things Java learned 25 years ago about how you organize the code. EVM right now is just a byte stream that you just point PC0 at 0 in the byte string, and you keep executing it, and you hope you don't jump into the data segment. So they'll have validation there to make sure that you're not putting in any instructions that aren't valid, that don't exist, that you have your data segment separated properly, that you don't try and execute code from your data segment. So these are the validation things that they're putting in. Another interesting thing that is being looked at, I'm not as sure that it's going to make it in this round, is auth and auth call, where you can sign a piece of data and you can let the EVM become that account. That's something that, is very exciting for something called meta transactions. But it's also kind of working around, not needing to have gas to run your executions, so to let someone else pay for your gas. And the reason they want other people to pay for the gas is Ethereum mainnet's expensive at times, very expensive right now. So, they want to use that to do their meta transactions. And on Hedera, we're going to, keep reasonably priced as a function of constant dollars. So that, if it makes it in or not, we'll be fine. And the last 3 EIPs are doing some VM opcode, and I spelled that wrong, so it's awesome. Opcode is supposed to be a D, not a C. Some opcode modernization with the way that it's set up. Everything is 256 bytes long right now. They're looking into shortening that, adding subroutines, and doing relative jumps and immediate value jumps. A lot of things that before the container format that couldn't be done because of the way that it's set up. So what's coming tomorrow? That's what we have today. We've actually shipped that. I hate these lights, just a second. We've actually shipped that last month in the 0.19 release of Hedera. And so you can actually use these beta 2 integrations today. As we go into what's coming tomorrow, we'll see why we really need some more of the features coming on, particularly some of the stuff Richard's writing, to really unlock the full power. So one of the things that we're looking to bring in January or later, this is not committed yet, but it's pretty far along the lines, is integration with smart contracts with the Hedera token service. The token service is great, but some people want to be able to do things like have a fully autonomous DAO and have a contract on the tokens and do all the work on the tokens that you might have an admin key to do. So with this API, we can create these DAOs. We'll support 5 operations. There's 11 different variations of it to deal with some ABI2 stuff. You might not want to use the ABI2 encodings. You might only want to stick with ABI1. So we'll support that. So we needed to expand some of these operations into multiple operations. But with this, will allow you to transfer, mint and burn, and associate and disassociate tokens with accounts. Doing this from the contract. And we'll let you do tokens and NFTs as all the token types that we support. And this will allow the contract to autonomously manage the token operation. So you can have a contract that will only allow tokens, allow 1 token to be minted a day. And that's literally what it does. So it mints the token once a day, puts something in the memory, and then when all mint calls will fail until it's called again. And there's no keys outside to manage this. So one can come up to the vending machine, pull the lever, get a token, and it's not going to recharge for another day. Those are the sorts of operations with smart contracts that you can allow, these sort of community things. And so here's the interface of what it looks like. And one of the things we tried to do with it is make it so that you can use these as naturally as you'd use any other function in Solidity. So here's the first example of what it would look like to mint 100 billion tokens. You would call Hedera token service.mint token. And this is some address that has the token that you have it in. I don't know what that exactly maps to, but you take the address of your token and you say 100 billion. So I want to mint 100 billion tokens. And the response will say whether or not it succeeded. If you don't have the authorization, it's going to fail. If you do have the authorization, it's going to succeed. And here's another example of how you can transfer tokens between accounts. This is a simple method where you give the from and the to. So I can say, here's the token I want to transfer. I'm transferring from myself to someone else an amount. And these compile into Solidity. And it's very natural Solidity to read, to interact with these. So when you put these in your Solidity code, it's going to be very natural. So yeah, we put some hard work into making sure that you can do the token service from within Solidity with minimum of speed bumps. So one of the things that we need to do, I mentioned authorization, is we needed to add contract key authorization. So right now in your contract, you can have Edwards keys, you can have multi-sigs, you can have complex keys. So we're adding a new key type. Actually, the key type's there. We're turning it on and enabling it. So that if a contract is doing the call into the operation, then the operation knows that I can do this. So you can put in your mint key, in your token, you can say contract 1234 has the right to call it from a call or a delegate. And so if you have that set in the authorization and contract 1234 tries to mint the token, it'll say, yes, we'll let you mint it. And if that's the only mint key in that token, then only the contract can mint it. We also in this support cryptographic keys. And the way that's going to work is that if you have a transaction and it requires a cryptographic key for authorization, it's going to check the cryptographic key of the entire transaction. So if the key signed the entire transaction, no matter what context level and what identity we have, we're going to check it. And if the transaction is signed by that key, it counts as authorization. And we can check between calls and delegate calls. And this supports some fairly complex operations, ways you can set it up. You can set up one of N keys. So you can list like 5 different contracts that can do these calls, and any one of them can do it. You can do 2 event keys. And what's interesting is you can require that not only is it authorized by the contract, but you must also have the admin key signing it. So you can require both authorizations so that you can sign it, and that you can, and so you can sign it, and you will be able to require the admin key and the contract to do it. So only Bob can do it once a day, pull that lever to get that out of it. And you can do nested keys, so you can do all of the crazy setups that you want, require 3 of 5 signatures on one branch, 1 of 7 contracts, and down the other. So we have a question coming from the audience. Will you be able to use the same EVM features that allow contracts to do token transfers? I.e., will the Basu code be similar in interacting with HTS? By allow, I mean giving them authority to make and transfer on behalf of an account. So that's going to be on my next slide. I think that's going to be an excellent segue. And that's asking a question of composability. So, so I was hoping that was going to be a question about, well, it kind of is a question about authorization. But I think what that's going to do is the next call. So for example, Hyperledger Basu, the code you would use in Hyperledger Basu is Solidity. So in one way, yes, any Solidity contract you compile will run on the EVM. And anything that you could run on Ethereum mainnet will run in Hedera. It's the other contracts in the system that are kind of more the question. Do you have the right contracts set up, and can you treat them like ERC 721 or ERC 20? So that's what the next ERC that I'm probably not going to make in January. It's going to be later, February, March, maybe April. We'll see. We need to get through the details of implementing it first. But it's HIP 218, and I think it just published today. So what this is proposing, it hasn't been approved by the council yet, but what it's proposing is that you can access your token accounts within Solidity as though it's an ERC 20 or an ERC 721 account. So here's a couple of examples of what the code might look like. If I have a token at 555, I could just cast this address of 22B, which is the address for account 555, cast it to an address, cast it to an ERC 20 account, and then as though it's an ERC 20 account, I can call the balance of operation on it and get the balance inside of the smart contract of the Hedera token service token. So that's one of the things this is enabling. Similarly with ERC 721, you cast it down. It's a slightly different syntax because they're different names. You do ERC 721 because that's the name that came in the spec. You cast it down, and then you do the call owner of. So I can ask ERC 721, who owns serial number 1 of my NFT? And it'll return the address. So if you have the contracts in Hedera, you can compose these smart contracts together like you would in the Ethereum mainnet world. And I think that's one of the strengths of the smart contract system of Ethereum that it has over a lot of the other smart contract systems out there, is the high level of composability of how you can do all of these interactions between all these other contracts without having to do a lot of coordination. They say their functions, they respect their functions, they do the smart contract, they will act like you tell them to, and they come out and they act. So this is the first step is we're going to allow, we're proposing is allowing you to interact with your HTS tokens as though they are ERC 20s and ERC 721s. There are some limitations. There are some things that the ERC 20, ERC 721 specify that HTS don't support directly, such as allowances where you can say, let this person pull this many tokens. There's other mechanisms that Hedera enables that lets you do that transfer. So, there's no total blind spot, but there might be different things different ways you would want to approach it that also have, better regulatory impact in the way that you're doing these things. And is that the next slide? Okay, so that's composability, where we're going to make the Hyperledger tokens act as though they are ERC 20 contracts. And the last subject that I have before I hand it off to Richard is to talk about gas-based throttling. And this is coming in with Smart Contracts 2.0. It's HIP 185. And this solves kind of an important ergonomic question, ERC 1155. We don't support ERC 1155 directly right now. That is a multi-token standard. It's something we can support. 777 is something we can support, but we're starting just with ERC 20 and ERC 721. So those numbers I rattled off are all of the higher and important token standards in Ethereum. So we're starting with the two most widely used ones. And then as we go further, we'll add more and more functions to these and make them respond to those functions. So that's an excellent question. And we're going to think about it. Does Hedera Smart Contract support BLS signature scheme? Not at this time. EVM doesn't support, well, EVM doesn't, Ethereum mainnet does not have a precompile for BLS signatures. If you want to write the BLS signature verification in a smart contract, yes, Basu will support it and Hedera will support it. The Basu EVM can support it if you write an EVM. I know the Celo blockchain, which is EVM based, has put the tokens in there. And Basu does have support for BLS 12. We could load it in as a precompile if we needed to. Will there be any sort of limit on NFTs issued via smart contracts as 721s in the same capacity as there are limitations on the number of NFTs that can be made with HTS? That's an excellent question. So each smart contract still has limited storage. We're looking at changing the storage numbers and moving them up once we get the database support that Richard's putting in. But that will be the limitation, is how much storage space you can use. So, 721's NFTs stored in the smart contract system won't have as rich a support as NFTs within Hedera. You can't require KFC. You can't require the custom fees. You're kind of bound in the way the Ethereum does it. So, yeah. How about Solidity fallback interaction with Hedera SDK? That's a transfer to contract, not H smart contract calls. So we also support fallback calls. In fact, that's how we transfer HBARs within Hedera. And I think in future versions of Solidity, they split back the fallback and the default payable. We also support that. So yeah, if your smart contract has a fallback function, we try and call it, it'll fall through to the fallback. And if it's payable and they've sent HBAR with that transaction, that HBAR will be transferred, just like as if it was Ether being sent to a fallback function. So when you look at the way that Ethereum works with its smart contracts with Ether, just substitute HBAR with Ether, and that's basically how it goes. The gas is paid with HBAR. Gas is denominated in tiny bars instead of gigaway. So there's some different ergonomics there with that, but it's the same sort of a situation. All right. And gas-based throttling. And this, I think, is one of the current biggest limitations of Hedera's support of smart contracts right now. Because right now we're throttled down to 13 transactions per second and 300,000 gas per transaction. Now, if you set it up properly, you can burn 3.9 millions of gas per second. And ETH right now burns about 1.2 million gas per second. But Ethereum also lets you burn up to the entire size of the block in gas if you feel the need to, which would be 15 million. So what we're proposing is switching, instead of on a transaction where we're going to limit the transactions and give each transaction a singular size, because we're going to limit the throttling based on the total amount of gas burned in the last second or two. And this, goes into the details of how throttling works in general in Hedera, but instead of counting transactions, we're counting gas. So the gas burned is summed up across all the transactions. You have a bunch of transactions that use 35,000 gas, it's going to work fine. You can get, check my speaker notes. If we could spend 5 million gas per second, you could get 147 of those. Or you could have one giant 5 million gas transaction per second if that's our limit. So, and that would consume all the time. Rather than limiting per transactions, we're limiting per gas burned. And so it's summed across all the transactions. And what's important to point out is that the query and view transactions are actually pulled from a different bucket. So if you're going to do a pure function or a view function, it doesn't work against the global transaction gas per second. If you're modifying state, then that gas per second is limited across all of the state. And for point of reference, ETH is about 1 to 2.2 per second, because they do 15 to 30 per block. They got something they've introduced with London with EIP 1339. And so they can go up to 30 sometimes per block, but the blocks come in only about every 13.3 seconds. So, as far as, you've got different ergonomics for the way that Hedera behaves versus the way Ethereum behaves. And we're trying to improve that with our gas-based throttling to get a more Ethereum-based like experience, while at the same time, preserving what's unique about Hedera and pushing the value of Hedera forward on that. Waylon, are there any other calls coming in?
No questions right now. You have absolutely been crushing it. So awesome work.
Cool. So I think Richard is next, and I will be on headphones for the next little bit too. So, all right. Richard, let me stop share and you can take over.
Awesome. Thanks so much, Danno. Richard, you ready to take it away?
Yes.
Awesome.
Is my screen up?
You look great. It's all you.
Okay, cool. Thanks. So yeah, so there's, as Danno was saying, there's a bunch of work that he's been doing to bring a modern EVM Solidity smart contract programming experience to Hedera. And a big part of that really comes down to some underlying internal details that a lot of people will never see. As an engineer, these have been extremely fun projects to work on. And I'm going to just kind of peel back a little bit and show a little bit of the sort of internal details of what we've been doing on the storage side in order to enable a really high gas per second limits. And although we haven't exactly told you what we are seeing in our test environments, we can say that we're looking at many, many times what you are getting on the Ethereum network for gas per second. But in order to do that, we needed to do quite a bit of work. So the work that we've been doing, we've sort of bucketed under this concept of a virtual Merkle tree, which allows us to scale to billions of records. Currently, Hedera stores all of the state in RAM. And so obviously we don't get by on very small machines. We run big machines on our mainnet that have a lot of RAM. But no matter how much RAM we feed them, there's a point where it just doesn't scale any farther than that. And smart contracts was one of those problems. So in our current implementation, actually stores smart contract data in a database. And there's a few problems with that, but one of them is that, well, there's two problems that you have to solve. One is if you're going to be storing that data on disk in some way, you have to have a very efficient way of hashing it. And another one is that you have to have a very efficient way of reading and writing individual key value pairs that live in that data set. Neither of those things are working today the way that they will after we make these changes to virtual Merkle trees. So here are the sort of problems that we needed to solve in order to create a virtual Merkle tree and for the sake of smart contracts or other sort of records that we might store in RAM today that could be stored on disk to allow us to scale to a just a phenomenally huge level. The first problem is that, of course, smart contracts do need to be able to store a large amount of state. So a lot of state. Whether we're talking about half a terabyte to several terabytes, there's a lot of state out there, and we're going to need to be able to store that. And it clearly isn't all going to fit into RAM. In addition to just the size of the state, it's made up of lots of little data members. So we need a database that can store literally billions of elements and still allow us to produce Merkle hashes in microseconds. And that's a bit of a challenge. That's where a lot of the fun came in. Our database that we're going to use needs to support some very important use cases that we have at Hedera. Reconnect is one of them. Reconnect is a feature that allows us to, if a node falls off or falls behind, it can reconnect and catch up with the rest of the network and get back to work. And for that, there's a lot of challenging engineering problems in order to make that work when we are talking about terabytes of data and tens of thousands of transactions per second, or in our case, millions of gas per second of operations. That's a lot of data drift that happens since your node fell off to when it comes back online. And we need to be able to reconnect all that in a very fast way, while the node that you're reconnecting with continues to churn through transactions at the same rate that it was before. So there's a lot of engineering challenges there. We also needed to design it in a way where startup would be incredibly fast. If you take a node down and then bring it back online, we don't want it to take a long amount of time for it to come back up. That has some impact on our upgrade times. And so it's important for us that our startup speed was really, really fast. And also, we save all of the state that we have once every currently configured 15 minutes. And we needed that state saving to be really fast, because while that's happening, while your node is saving its state, we can't slow down the transaction speed that we have going on. So there's a lot of things that are going on in this node concurrent with handling smart contracts or crypto transfers or HTS transfers or minting, burning, and everything else that's going on in the system, or the consensus service, handling messages. And there's a lot of stuff going on in the system. And we need to be able to have a database that lives in that world and is very, very efficient. And as I mentioned, we need to be able to hash a tree really efficiently. So before I go to the next slide, one thing that I want to mention is that we did not start off with the intention of writing our own database for our virtual Merkle trees. We started off by evaluating everything that was on the market. Everything that other chains were using. We looked at a number of different databases coming out of Google and Facebook and everywhere else. And none of them hit all of our marks. We benchmarked them, we profiled them. And fundamentally, the problem was that having our own database meant that we could craft it for our exact use case, which meant that we didn't have to have, for example, locks and concurrency controls in places where we didn't need it. And we could put concurrency controls in places where we did need it. For the most part, we tried to write a completely lock-free database system that worked with concurrency, but we were able to do that because we knew exactly the query patterns and the write patterns and everything else that was going to be used. So we did end up writing our own custom database, and I'm going to give you a brief sort of look into what we ended up doing to do that. And I do say brief. I mean, quite honestly, we could do this one for 3 hours. There's a lot that goes into it, but I'm going to kind of give you the overview. So the first thing I'm going to do is kind of describe what do I mean by a virtual Merkle tree. Well, I think probably everybody on this call is familiar with what a Merkle tree is. Our Merkle trees have a couple interesting characteristics. The first one is that it's strictly a binary tree. While the in-memory Merkle tree that we have at Hedera is an n-ary Merkle tree, the virtual Merkle tree is strictly binary. And this was actually a very important thing that we did for performance and efficiency, because it allowed us to very efficiently label the paths to every single node in our tree within just a long. So it was nice, compact, and simple, uses very little memory and so forth. So, and to be completely fair, it didn't have to be binary tree. Technically, it just needed to be a full base true tree. So it could have been binary. It could have been an octo tree, an 8-way tree. It could have been a hexary tree. Any of those would have worked as long as it was full. But there's some downsides to those other trees, and there's some benefits to that, which is a little bit too much to go into in this particular presentation. But needless to say, we're using a binary tree. Our binary tree is entirely stored on disk. We will bring portions of it into memory when we need to, but conceptually, you can think of this tree as being completely on disk. In terms of terminology, our tree has a root node and a number of what we call internal nodes. In the past, I've always called those parent nodes. Sometimes we call them interior nodes, but they're all the branching nodes in the tree, the non-leaves. And then we have leaf nodes. And the leaf, I should say, on the internal nodes, they really only have two things. They have a path, and then they have a hash. So in this diagram, you can see the paths. In our system, the paths are always incrementing top to bottom, left to right in the tree. So it starts at 0 and auto increments all the way up, no skips. at all. And so each one of those internal nodes has a path. You can see it's 1, 2, 3, 4, or 5 in this case, and it also has a hash. The leaf nodes also have a path and a hash, but they also add a key and a value. So in our example here, we can see that the apple leaf has the key is an A, the value is apple, and the path is a 7. So that's what we see in our diagram here. And there's actually two other things in this diagram that are worth describing before we go to the next representation. You'll notice that I've used, first off, the entire diagram is at 50% transparency, because whenever I have a transparent node in the diagram, that means that it is on disk and not in memory. And the other thing is that you'll see the dashed lines instead of solid lines. That's another way of indicating that it's completely on disk and there's no concept of it in memory at all. So in our first diagram here, we have a tree with 7 leaves and a total of 13 nodes, 6 of which are internal or root nodes. And they all have their paths and they're all completely on disk. So with that, I'm going to just kind of walk through an example of what the tree looks like as you're building it up. And I know I haven't, right now I'm going to talk about sort of the theory of how this tree is operating. And then I'm going to show you how it gets married up to the disk and what the database is doing on disk. So to start with, let's have a basic tree that has absolutely no leaves on it. So that'll just have a root node and that's it. And if you were to ask it for a hash, it would have a hash, but it would be the hash that represents null children. It's the null hash. Now let's add 2 leaf nodes to this tree. So I'm gonna create my first one by adding this apple node, or I could call it the A node, whose value is apple, and it initially takes the left position of as the first child. Then I also add the B leaf, and that one's going to take the second position. So I added A first, and then I added B. And in the diagram, I've marked them both with a green check, meaning that they are new this round. They have not yet been flushed to disk. They have not yet been hashed. They're just, I've run a transaction that created these 2 new leaves. And so here they are. Now in the same round, maybe this is the next transaction, but in the same round, I'm going to add another one. I'm going to add cherry. So when I add cherry, it moves the apple from path 1 to path 3, and then it adds in cherry at path 4. As I said, this is always a full tree. It's going to be always full and balanced. So when we wanted to add our third leaf, we had to introduce an internal node. We just take the first leaf that's in the tree and move it down and create an internal node in its place, and then add the new node at the end of that. So this gets us to the next step where we've grown our tree. Now, the interesting thing here, just in terms of our diagram, is to note that both root and leaf 1, internal 1 on that first path, neither of them exist in memory. They're just figments of our imagination at this point. They actually don't exist on disk either, because we haven't saved them to disk yet. So they're just complete figments of our imagination. They have no representation anywhere in the system yet, except conceptually. All that really happened, quite honestly, is that we just have these 3 leaf nodes with no parents, no nothing. They're just 3 little records that say, I'm a leaf. And they have, and we just manipulated what the paths were that were set on those leaves as we moved it around. That actually is a really important performance optimization. Whenever you have to walk up the tree to say mark parents or create parents as the tree is being mutated, that's a log n type of operation. Whereas what we did here is constant time. And so when you're doing a rapid manipulation of the tree, we save a lot of time, a lot of computational overhead is saved by just imagining that there's some internal nodes, but not actually dealing with them yet. In fact, we don't need to deal with them yet. The first time we have to deal with them is when we hash. And when we do that, we can visit each one of them exactly once in the most efficient way possible. So we never end up with that logarithmic problem of manipulating the tree, because these internal nodes don't actually exist yet. That is interesting. So let's go step 4, and we just add all the rest of the stuff to this tree. So I built it out. I added them A, B, C, D, E, F, and G in order. And if you did add them in order, they would end up in this location just because of the nature of the algorithm and as it's balancing the tree. So I now have all my leaves in here. Again, all the internal nodes are all fake and phony. None of them ever existed. I never marked any of them dirty. I didn't create any placeholders. I didn't manipulate, who their children were. I didn't manipulate pointers to parents. I didn't have to do any of that. All I did was just manipulate the leaves themselves and changing what their paths were based on where they should appear in the tree. And that was it. So the next step is to actually hash the tree. Now, during the hash process, you'll notice that all of the, in the diagram, everything became fully opaque, 100% opacity and all solid lines. These things now all do exist in memory because during the hashing process, I needed to take A and hash it. I needed to take E and hash it. Then I needed to take those two hashes and hash them, and that becomes the hash for 3. So now 3 must exist in memory so that it can hold that hash. And then I did the same with 9 and 10, which created 4. I hashed 3 and 4. I took the hashes from 3 and 4 and hashed them to get the hash for 1. Did the same thing on the right side of the tree. And then I had the hashes for 1 and 2, which I combined, hashed, produced the root hash for root node 0. Standard Merkle tree stuff. Now I just described it in the depth first order. We don't do depth first. I'll explain that another time. I don't think I have time for it in this call. But we have actually developed a very efficient hashing algorithm that does not require depth first traversal, which is also interesting for some of the performance optimizations that we did. So now that I've hashed the full tree, I'm ready to flush it to disk. So now we go through a step where we flush everything that we had in memory gets flushed down to disk. And so now in my diagram, everything is back to being transparent and back to dashed lines. All this stuff is on disk. Now that I've got a tree that I've built up and I've saved it on disk, this is kind of back to our first diagram. Now I'm going to make some modification. I'm going to go change A from apple to ant, and I'm going to go change B from banana to bear. So when I go do that, you will notice in our diagram that certain nodes in the tree still have the dash line and are transparent. They're completely on disk and aren't even part of our imagination. We don't even care about them. They're completely on disk. Some of them are totally opaque, obviously A and B, because we changed those. So those are in memory. And the other ones that I have that are still transparent but solid lines, that would be root 1, 2, 3, and 5. Those have not been read from disk. They're still on disk, but they are sort of in our mind, imaginary, virtually in memory, but they're not actually in memory yet. They're just a figment of our imagination, but we know we're going to need to visit those when we go and do our hashing process. So we sort of conceptually they're there, but again, not actually using any bytes in RAM to represent those things yet. Okay, our next step is we got to hash this tree. So when we go do the hash, something does happen here. And I didn't have a fourth way to diagram this, so I'll just describe it. When we hash 3, for example, we do need the new hash from 7 from A, and we also need the existing hash from E. So when it comes time to hash 3, we recompute the hash for A first, and that becomes available for 3. And then we go load the hash from E from disk. Those two hashes are then hashed together and produce the hash for 3, and so on up the tree as we go and visit. So although some of the data on, let's go the next level up. When we look at 1, 3, and 4, when we need to produce the hash for 1, we can take that new hash that we just computed for 3 and use that. And then we go load the hash from disk for 4, and we're good to go. We don't ever have to touch 9 and 10. So we do have to go load some stuff from disk, but we don't have to load all the stuff from disk. In fact, it ends up being a very, very small fraction of what's on disk needs to get loaded during the hashing process. And then once we've computed all those hashes, these objects now, 1, 3, 2, 5, root, those things obviously are in memory now because we just computed new hashes for them. So we have to hold on to those then. But we don't hold on to them for very long, and then they get flushed to disk. And we're back down to this sort of a state. So hopefully that was helpful in sort of establishing a mind frame of where we're coming at with the virtual tree. The idea is that it's really virtual. We only bring into memory the stuff that we need. It only stays in memory long enough for us to hash it, and then we flush it to disk. In our system, we will do a whole batch of transactions as part of a single round, if you will. And so we'll handle a transaction, read some stuff from disk, handle a transaction, read some stuff from disk. And then after some number of those that get handled, we then hash it and then flush it to disk. And to be completely honest, it's a little bit more complicated than that. The disk is most efficiently used when you have a nice chunk of stuff to flush. So we actually don't flush single batches. We batch up batches and then flush the whole set down to disk. Well, that's good. But what it does mean is that we do have some kind of in-memory cache that we need in order to keep track of the things that are in memory until we're ready to flush them back down to disk. Another thing that's worth mentioning is that disks, even modern NVMe disks, hate random writes. And they don't particularly like random reads either. Now, initially, we thought that NVMe was going to change the game. It's basically memory. We should be able to just do random reads, random writes, reads and writes. It should be very much like our in-memory tree. Turns out that's not the case. There's a lot of drivers. There's a lot of caches. There's a lot of things between the top level of the stack and the actual disk itself. And it still fundamentally works best in the way that we would traditionally use a disk, where you do large batches of sequential writes and sequential reads. If you can map it into available memory, it's a little bit of a different game, obviously. But if we could have done that, we wouldn't have been doing this in the first place. So the other funny thing about that is that initially our benchmarks were just phenomenal doing random reads and writes on NVMe disks. And we thought, hey, we're golden. And we let that benchmark run for 2-3 hours and performance fell off a cliff. Because what happened was that there were all these caches between us and the actual disk, including caches on the disk itself. And all those caches, once you filled them all up, it could no longer pretend, and it had to actually sort of slow down or apply back pressure so that it could do the actual writes to disk before you did your reads. So there are limits. And at the scale that we're talking about, with tens of thousands or more of transactions per second and billions, terabytes of data, it's just too much for all those caches. And so we had to learn how best to make use of it. Even modern NVMe disks, we had to, we learned that the best way to deal with it is by using sequential, batch writes and sequential reads. And so our system is based on that. So real quick, the in-memory cache representation, this was also an interesting engineering problem because we needed to be able to maintain multiple versions of the tree in memory, because I showed you, as we built up the tree, 2 different flush steps, right? There was one where we built the whole thing up and everything had a fruit or vegetable name, and then we flushed it. And then I had another one where we made changes to A and B. And the truth is that when we're doing some complicated things like, say, state saving or reconnect or even hashing, we will have one copy of the tree that we're hashing while another copy of the tree is applying new changes to it. So we needed to have an in-memory cache that was versioned and also extremely lightweight. So this is just a very, very simple oversimplification of the in-memory cache. But essentially, we had and there were several of these, but this one is the key to leaf map that's part of the cache. So there's basically a hash map. You look up your key, and then there's a linked list of versions, essentially. So if you were the version, if you had a copy of the first version of this tree and you asked it a question, it could get you back the right answer. If you had a copy of the second version of this tree and asked a question, you could get back the right answer. So this is essentially the in-memory representation. And there's not much more to say about that. Now, the on-disk representation is another story. This one is quite interesting. We needed to be able to store the data on disk, like I said, in a sequential big batch set. And we can't do random writes. Random writes are going to kill your performance if you're doing it at the sort of scale that we're doing it at. So what that meant was that we were going to need, if you had the first set of leaves and we wrote all those out, and then you were going to make a modification to a couple of the leaves, we couldn't go back and update the rows that we had previously written. We just can't do it. There's actually some other very important reasons why we went with this architecture in terms of the startup speed, the save state speed and reconnect capabilities that are a little too deep for the description that we're doing tonight. But essentially what we did is we said, okay, every time we flush to disk, we're going to produce a new immutable file. And it's always going to be sorted in path order from lowest path to highest path. And we will just keep producing those things. So in this case, I'm showing you two different data files, data file 0 and data file 1. In data file 0, it had all of the initial updates that we had for path 6 to path 12. And in this case, I'm just showing the leaves. We also have corresponding tables for storing all the internal hashes, because we do need to be able to read those from disk in the future when we're doing hashing. So, but this is just the leaf example that I have here. And so you can see that that first flush we did produced this table here with a whole host of things from path 6, 7, 8, 9, 10, 11, and 12. And we also needed to have a couple of indexes, and these indexes we actually store in memory, in an off-heap memory, in a very, very efficient manner. They look less efficient on paper than they actually are in RAM. It's actually there's a bit of work there as well. But what these maps essentially allow us to do is that if you say, hey, I need to go get the hash for endive, then what I'm going to do is I'll go to my one lookup table and I'll say, well, an E is at path 8. And then I'll go to my path to file location index, which says, aha, path 8 is in file 1 and at byte offset 200. And so then that takes me to my data file 001, right there where my path is at, assuming that I had 100 bytes per row. In reality, these are variable length lines. So they don't, they wouldn't really be at 100 byte increments, but in this case, just to make the diagram a little easier, that's what I went with. So what this means is that when we are cranking through looking things up, it's very cheap. We do 1 or 2 lookups in RAM, and then we go to the exact spot on disk and read the piece of data that we need out of it. So we are doing random reads, but we're not doing random writes. Then when we did our modification, we created ant, we updated A to be ant and B to be bear, and then we flushed that down. That ended up creating another data file. And when we created that data file, we went back and updated our indexes in memory so that they now point, path 7 points to the new file and path 11 points to the new file in their new locations. So that's essentially what the on-disk structure looks like. Now, the problem with this whole thing is that we're going to be leaving a bunch of trash on disk, because every time we go modify a value, it ends up creating a new file. And that means that there's data in an old file that's no longer useful. So another essential characteristic of the system is compaction. The database needs to be able to compact out the old data that's no longer needed. So we have what we call small, medium, and large compactions that we do. Small ones happen every few seconds. They gather up the small, most recent files, and they merge those together and compact out all the stuff that we don't need anymore. Then we have medium ones where, and these are all configurable, but our current configuration value is like every hour, we'll go find the small medium files and merge those together. And then once a day, we'll go compact everything together. So that allows us to have this really important characteristic that each one of our files is totally immutable. We never modify a file once we've written it, but we do have a way to compact them and produce a new file. And then once we're done with that new file, we can delete the old file. And that gives us a lot of safety and concurrency when if the system crashes, or if we have to do any type of a reconnect and there's a long-lived process that needs access to that data, it can access that data even after we've done the compaction. And then when all processes are done with it, the file disappears, all that kind of stuff. So the compaction was a really important part also of our database. So that was a lot. I got through it. I just
Richard, nice work.
Thanks. I just wanted to put in a plug. If you like Hedera, go find our GitHub projects and star our projects. Make my day. And hopefully one of these days we'll be able to do another deep dive and get into a lot more of the nitty gritty details because there's a lot more depth that we could actually go into. But I guess it's just sort of a parting thought on that is just that we've been putting a lot of engineering work into solving these problems, and we're really pleased with the way that it's come out. And it's going to give us a tremendous boost in performance over our previous smart contract implementation, a tremendous boost over our previous smart contract implementation. And coupled with all the new capabilities and features that Danno has been adding to really enhance the programming experience, there's a lot of really great stuff coming down the pipe, and we fully intend and are competing hard to be a premier platform for smart contracts. So with that.
Awesome. That was really good. A lot of really awesome, amazing information there. How do you feel about some questions?
Yeah, I'm totally good for it. Yeah, sorry, I was in full screen, so I couldn't see them. Let's see.
Okay, I can read them out to you if you want.
Okay, does it start with the Merkle trees on all nodes in sync?
I think the first one we got, yeah.
Okay.
There's one other one, but Danno wanted to answer that one, so we'll touch on that one last.
Okay, so the first question is, do you need to keep Merkle trees on all nodes in sync? Yes, it is a fully deterministic. So all the Merkle trees on every node needs to be in sync. They need to produce the exact same hash every single time and do it deterministically. So in order for that to happen, they have to have exactly the same values for all the nodes. The trees have to be the exact same structure and configuration. Everything has to be exactly the same. Question, does this mean that you have batch fast copies of state of the Merkle similar to what Swirls did? Yeah, it's exactly the same. In fact, all this stuff that we've been adding we've been doing it in coordination with the Swirls team. So it is the same conceptual framework as what Swirls was doing. The only difference is that we are now doing it on disk instead of in RAM. In fact, the code for a big chunk of this stuff exists in the Swirls repo and will be part of the next open access release that they release. So yes, it is essentially doing fast copies, which was where a lot of the interesting engineering challenges came from. Would a RAID parity configuration help with the response time from storage, or would that add time to latency? That's a really good question, and I don't know yet the answer. So we did do testing on both network attached storage, and we also did testing with RAID system and striping in particular, and we didn't really see much of a performance difference. But I think we do have some ideas that we're going to be pursuing in the future as we continue to work on this, around actually having different volume mounts for different of the use cases that we have and a few other scenarios. But that's a really good question, and I don't have a good strong answer for you on that one yet. Did we write our own caching driver? No. So we're just running on top of the stuff that's the operating system is giving to us. The caching that we are doing in memory I wouldn't characterize it as a driver. It's more of just for being able to keep these fast copies in memory for the other operations that we needed to do. We store those in RAM, but we did not write our own device drivers or anything at that level. After which implementation will the community be able to program DeFi dApps on the mainnet? That might be a good Danno question.
Yeah,
Danno,
I'm here. I'm just getting into a different room where I can speak.
Yeah, he's load balancing.
Yeah, I am. I'm playing video. Actually, my son's playing video games at a tournament. So with DeFi, we still have a little bit more to go. There's something called the create to operation that we don't fully support yet. And work is underway on that. I don't want to commit to it quite yet, but I'm optimistic. It solves a couple of problems. So I think that's the number one problem of putting SushiSwap or Uniswap on Hedera directly right now, is that create to operation. So once we get that fixed, you can do any operation the way you would do it. But the trick at that point is, how do you connect to mainnet? Because it's not even like a layer 2, because it's not dependent upon mainnet. So you need to write a token bridge to go between Ethereum mainnet and Hedera. and there are solutions out there, and you can implement those with smart contracts.
I can touch a little bit on this too, actually, because not all DeFi applications actually use the create2 opcode. Actually, one of the things that one of our engineers had me do was to compile a list of all these different DeFi protocols and figure out which ones use the create2 opcodes and which ones did not use the create2 opcodes. So when it comes to decentralized exchanges, most of them do use the create2 opcodes. But when it comes to things like lending, platforms like Aave and Compound, you can totally deploy these smart contracts on Hedera, and they don't use the create2 opcode. So the answer is there are some things that are going to be, some DeFi applications that are going to be able to be available as soon as we have the Hedera token service precompile, and then it's going to have a really large increase in quality when the virtual Merkle tree optimization comes online. And then next, like we're working on, is getting that create2 opcode supported. But that's what I know about that one.
Should we bounce up and ask the other question for Danno, and then we can go get the last one that just showed up?
It was the question, contract update transaction.set bytecode field was removed recently. Can you still upgrade a smart contract without using a proxy contract? And so you couldn't do it before. That was actually not changing the bytecode. That was changing the field we removed was changing the contract that you asserted was the init code for that bytecode contract. Not even the contract, it was the file that you assert it came from. So it wasn't actually changing the bytecode on Hedera. And we removed it to remove the confusion, to give the impression that you could update the bytecode. And right now, contracts, just like Ethereum, just like all other EVM, unless you do self-destruct and find some way to reuse the address, which you can't do right now in Hedera, then there's no way to change the contract code at a particular address. So that's why I removed it, so we're consistent with the rest of the EVM ecosystem, that the code that doesn't have self-destruct in it is never going to change and never going to go away, pending state expiry and stuff like that. So that's why we got rid of it. It never functioned as it implied before. So rather than give that implication, we just went ahead and deprecated it.
And that's actually a really important key. That's like by design. Smart contracts, it's very important that smart contracts are immutable. I mean, think about if you were using a huge DeFi protocol that has billions of dollars of assets locked in value, and somebody decided to modify the contract just randomly. So it'd be a massive liability. The whole advantage of these smart contracts is to allow a totally trustless, totally autonomous system that you can trust is going to behave the way that the code says it's going to behave, and it's not going to change. So just some emphasis on the fact that the immutability of smart contracts is, in fact, incredibly critical.
That's a feature of the system. Yeah.
Yeah.
So the last question on here is, you mentioned state is saved every 15 minutes. What considerations were taken into account to arrive at 15 minutes, and will that ever change? Yeah, so I should clarify that a bit, because I thought that when I was saying it, I was like, oh, actually, I don't think people have the context for what I mean by state saving. So so there's a couple of different meanings of the term saving the state. One meaning would be once it's sort of final in the scene graph, that happens right away. I mean, as soon as the transaction is done, the state is persisted in the, call it a scene graph. That's my old history coming up. Once you have updated the state, it is saved in the Merkle tree. And so in a sense, you could say that is saved state at that moment in time, which happens just immediately upon completion of the transaction. There's another saving of state, which is when we write the state to disk the first time. Now, in the existing Swirlds platform code that Hedera uses, when it actually maintains all the Merkle tree in memory until every 15 minutes, where it writes it down to disk. And that number is totally configurable. We could change it anytime we wanted to. We can make it longer. We can make it shorter. It has no impact on the safety or security of the system. What it does is it gives us an opportunity to take a snapshot of that data and we upload it into some Amazon Glacier type of tape backup system so that we have, you know, a hard copy of what the state looked like at that moment in time. If there, and you know, heaven forbid there ever is, if there were ever a catastrophic failure, 15 minutes means we will never, ever, ever lose more than 15 minutes worth of stuff. But as we add more nodes to our network, that you know, the probability sinks dramatically. And as we add community nodes and other things on our network, it becomes almost impossible to even consider that happening. But if it were to ever happen, that 15-minute window is basically what that's used for. The other, so for the virtual Merkle, we save to disk way more frequently than that. We save to disk, it's like every few seconds, maybe every 15, 20 seconds, maybe once a minute. It's a much slower, and I'm waffling on that a bit because we actually save every 20 rounds. That is our current configuration. And how long is a round? Well, depending on network load and other things, it might be, you know, 10 rounds a second. It might be around every second and a half. So, you know, I'm hedging a bit there, but it's, you'll find in practice that it's somewhere between 10 and 60 seconds we're flushing to disk. And then every 15 minutes, we collect all the stuff that we've already written to disk, plus the things that are still in memory, combine it together, that creates our saved state, which is saved on disk and then uploaded to a nice, safe, you know, distributed system where we can retrieve the data at a later date. So that being said, in answer to your question, the 15 minutes was basically a window short enough that that it's highly valuable, but not so short that we are creating, you know, petabytes and petabytes and petabytes of data that we have to upload to some tape backup storage system. So there's some balancing act there, but the number doesn't have any effect at all on the safety security of the system while it's running and operating.
Awesome.
Cool.
Let's see. Do we have any other questions coming in here? Okay, awesome. It looks like that is all for today. Huge thank you to Richard and Danno for giving us some of their time and explaining some of the engineering problems that they've been working on. I know it's super valuable to our developer audience, and we definitely hope to do this sort of thing again soon.
Cool. All right. Thanks, everyone. Thanks for the questions. Bye.
Sweet.